Go ahead.
Good afternoon and welcome back to our Asteroid Initiative Ideas Synthesis Workshop. Our session this afternoon is on the crewed mission systems, and we really encourage those out there to participate. You can send your inputs into Twitter at the hashtag AsteroidCrew, and then you can follow online as well at the Asteroid Initiative and then at www.nasa.gov Asteroid Workshop. I really thank everybody for making the presentations available. We had 22 total submittals, and we'll talk about 13 of those today. I'm going to talk a little bit about what we've been doing on the NASA side relative to the crewed mission segment before we get started. So we've had a team off working the mission concept for the redirect crewed segment for about 10 months, and that has been a multi-center team with participations from the Johnson Space Center, the Goddard Space Flight Center, the Glenn Research Center, the Kennedy Space Center, the Marshall Space Flight Center, and the Langley Research Center. And we've been focusing on putting together the concept. We're very excited today, though, to hear your ideas. I think you've seen the overall mission concept where we would send Orion out to the asteroid, and we would rendezvous with the robotic asteroid redirect vehicle spacecraft. We would perform 2 spacewalks of approximately 4 hours in duration with 2 crew members. We would get the samples as shown in the lower right-hand slide with the astronauts performing the spacewalks and then return those in Orion. And one of the things we've found as we've worked through this mission is Orion is kind of the perfect vehicle for this flight. We've strived to make this a very affordable mission, and so our approach has been to utilize a lot of hardware in existence, which we'll talk a little bit about, and to try to minimize changes to Orion. Orion is an ongoing program that's under development, but what we found is Orion is very capable. Even though it wasn't intended to do spacewalks as its primary mission, we can actually do spacewalks using Orion as the airlock. We also are trying to minimize changes to the Space Launch System, which is under development, and it's a perfect vehicle, a perfect rocket to provide the launch platform for Orion to go to this distant retrograde orbit, meet up with the asteroid, and then execute the spacewalks. So we've spent a lot of time, as we have developed the mission, striving to be very affordable and using a very low-cost approach, and I'll talk a little bit about that. Of course, here's the EVA scenario. You can see this graphic that shows 2 astronauts working from one working from a boom platform to open up the bag, then closes the asteroid and perform the spacewalks. And I show this graphic because a lot of the discussion today will focus on the spacewalks, on the tools, on anchoring techniques, on potential robotic ways that we could execute the spacewalk. And so a lot of the session today will focus on those things. Here we show some of our concepts, and this shows affordability in terms of some of the things that we've developed to execute the spacewalks. We have 4 kits that would go into Orion to help augment the capability. The first on the left-hand side of the chart is the EVA servicing and recharge kits, which are, the suit itself is derived from the shuttle modified AIISW, but we would use servicing techniques that we use on space station today. We leverage those capabilities to service the suits in between EVAs. On the next column, you can see some of the tools that we might use, and these leverage heritage from both shuttle and space station. And then our communication plan would leverage a lot of the advanced exploration system suit work that we're doing today, in addition to when we bring the vehicles together, the docking system work that's being developed for the space station for commercial crew. And then even in terms of repress in Orion, after we depress the cabin and execute an EVA, when we repress the cabin, we would use a very simple pressurized container developed from the shuttle or the space station, nitrogen-oxygen recharge, a similar concept to repress the cabin with air. So we've put together these very simple techniques to do an early mission with Orion. And then the first part of our session today is going to focus on how we feed forward. It's very important as we put this mission together in an affordable fashion that it leads to future exploration missions. And we see this mission in 3 different dimensions. One is maybe in the near term, we're going to continue to work in cislunar space with extended duration missions in cislunar space. You see on the left-hand side a kind of a notional exploration augmentation module that we would fly up after the first mission and could do extended duration spacewalks, stay at the asteroid a little longer, or do other science in cislunar space. The middle graphic shows a potential path to spiral down to low lunar orbit and do operations in the lunar vicinity. And then, of course, our ultimate destination is Mars, putting together a combined spacecraft to go traverse to Mars in the 2030 timeframe. So with that, I think we'll take our first presenter. We'll follow. You can follow along on. Is it shown here on the charts? Whoops. Somehow we are having a little graphic issue. So again, you can follow along online at the nasa.gov Asteroid Workshop in the hashtag, and we'll get into our series of discussions. We had 22 RFI inputs again, and we have 13 today. Those were selected for the merits for this mission, extensibility to future missions, which will be the first topic that we'll cover, and then design maturity. And then our first presenter is from the Boeing Corporation, Mike Rafferty, and he's going to talk a little bit about an exploration augmentation module and how we would use that to augment the mission. Mike?
Well, thank you, Steve, and thanks to the LPI and to NASA for inviting us to speak. We really appreciate the opportunity to talk. I'm actually presenting Matt Duggan's charts. Matt wasn't able to make it today, so I'm kind of a stand-in for Matt. So hopefully you'll be patient with me on questions and details a little bit. What I'm going to talk about today is an idea for an asteroid exploration module. So this is really directly addressing extensibility. And the basic idea is the asteroid mission is really the first step of many steps that we're going to take in exploration, with Mars really being the ultimate destination that we're after. The asteroid mission, we want to configure in such a way that we'll be able to feed forward into the Mars mission as best as possible. So that's really what the whole idea behind extensibility is about. And so the idea behind the asteroid exploration module is that this is something that will really enhance the extensibility to subsequent missions to Mars and other destinations. But it also has direct benefits to the asteroid mission as well. So I'm going to get into mostly the benefits to the asteroid mission. Maybe if there's time, we'll talk a little bit about the more extensibility benefits as well. I'm going to go over 3 different concepts, and I'm going to just give you a highlight of what they are on the next few pages. But before I do that, why focus on this kind of thing? So the basic idea behind this kind of extensibility is to try to improve, for the asteroid missions, try to improve the safety of the mission. As we all know, this is a very challenging mission. It's going to have very tight timelines on its performance and execution. The performance of the vehicles themselves are very close to what we need to execute the mission. So anything that we can do to improve those margins, both in terms of time and system capability, are going to improve the safety for the crew. The second thing they're going to do is they're going to improve the probability of mission success, the chance that we're going to be successful in accomplishing all the objectives of the mission as well. And a lot of that is done through the addition of capabilities like airlock capability or additional supplies, additional gas, fuel, the ability to maneuver, food and water and things for the crew to allow them to stay longer. All these things are very important for the success of the asteroid mission itself. And of course, as it says at the end there, the extensibility to future missions is really directly relevant as well. So what I'm going to do next is just kind of walk you through each of these 3 different options that we've looked at Boeing. The first one is really an international option. This is something that we've looked at together with a company called Energia in Russia, and they are experts on spacecraft. They were one of our partners on the International Space Station, so they have a lot of experience. We have a lot of experience working with them. And this concept that we're showing here is really a derivative of a new module that they're working on for space station called the Science Power Module, SPM. So the idea here is to build a version, so we would test the SPM first on the ISS, and then we would build a version, the Russians would build a version of the SPM that would be geared towards the asteroid mission and would be used for that mission specifically. So there's a timing sequence there, and it would depend on whether the timing worked out for when the asteroid mission would be executed, and the relationship with the ISS mission that they already have planned and on the books. But the basic idea is build another copy of what they're doing there, a few modifications to enhance its use on the asteroid mission. But this would be something that would require that we have a negotiation and agreement with the Russians that they would do this. But it would bring international participation into the program, very important. Okay, our second option is really based on equipment that we have that's residual from the Space Shuttle program. So this is US equipment. There's an orbiter airlock that was part of the shuttle program. Actually, there were two of them. And we have these stored as residual assets at NASA in Kennedy Space Center. And so if you look at the part, I'm going to test out the little pointer here. Oh boy, that is bright, isn't it? So this being the capture spacecraft here, and you can see the asteroid captured here, this is actually the orbiter airlock here, and what we've done is we've augmented the orbiter airlock with some additional systems to allow it to be able to exist in cislunar space and be able to be on its own, okay? And then it would have a docking interface that would then dock to the spacecraft and would dock to the Orion. It would allow this to be used for an airlock, and would be additional capability that we could store supplies and relieve the requirement on the Orion to have to do that EVA. Okay. The third option that we looked at also looks at residual assets that we have, and there's actually two variants of this one. One is we use a residual node asset that we have from the ISS program. Another way to do that would be to have the Italians who built the nodes for the ISS program build a newer, lighter one. And the trade there is the one that we have is a little bit heavier. They could build a newer one, but it costs more money, so it's a capability versus cost kind of a trade. And then we would augment that with a bus capability that would allow it's essentially taking spacecraft systems and allow that this node would be able to operate. So the reason that you want to have nodes is because for future missions, it's going to be very important to be able to dock multiple spacecraft to where we have the asteroid or wherever we go to next in our next step after the asteroid mission. So I went through the three concepts that we have at a really high level. I know I'm probably getting a little bit shorter on time. So what this chart tries to do is really just go through what are all the capabilities that we're looking for from the mission, and it shows that you can meet most of what you need with just the Orion, and you pick up some really significant ones if you add an exploration module. So this is really talking to benefits to the asteroid mission, but of course one of the primary benefits is to what comes after the asteroid mission. And so in summary, improving safety for the crew, improving success for the mission, for the asteroid mission, and then being able to support future missions that come after the asteroid mission. So how'd I do on time?
Excellent.
We've got time for questions?
You good? Excellent. Yes, we have some time.
So thanks, Mike. So we do have time for a few questions. If we have any questions, virtual questions or questions here in the room, you could address those to Mike or myself or Mark McDonald, who has served as our concept analysis team lead.
Well, I had one question for you, Mike. So did you consider the delivery of these elements to the DRO, and if so, what launch vehicle did you assume?
Yes, what we looked at, Mark, is that these are fairly large elements, so SLS would be the logical way to deliver these. It would be possible maybe to look at delivery to low Earth orbit and then using some kind of a tug to move, but that's actually probably more expensive and would take longer than just a direct injection with SLS.
Agreed. Thank you. Any other questions? And for those of you online, we hope that you can submit your questions as well to our moderator, and they will forward those to us, so please participate where you can. Michelle, you have a question, ma'am.
Are there, is there a concept of operations for automatic rendezvous and docking prior to the Orion actually arriving
Yeah.
with the asteroid spacecraft?
Sure. Yeah, Michelle, I think that many of the systems that are going to be needed for the spacecraft to rendezvous with the asteroid are the same kinds of systems that you would want to be able to rendezvous between two spacecraft. In fact, if you think about it, rendezvous between two spacecraft is actually a little bit easier than it is what we're trying to do with the asteroid mission, because the asteroid mission is a tougher target. And whereas two spacecraft, we actually control them both. With the asteroid mission, we only control one of them. So we would use the same systems.
So even though they're residual hardware, you could outfit with additional?
Yes. Yeah, we would retrofit. There would need to be modifications made to this residual hardware in any case. So yes, we'd retrofit it.
So Mike, I have a question. So it looks like from your concept, you could execute this in a number of different ways. You could fly the reference redirect mission that we've talked about, flying the crew up first, and then you could fly perhaps this airlock tunnel adapter up as a second. Is that kind of what you're thinking?
Yeah, I think so, Steve. I think there are different options for how the mission could be done. You could separate the launches of these elements. You could even look at launching one of these elements together with the asteroid redirect spacecraft if you used SLS, because it's large enough to be able to launch both, probably. So.
And your plan would be, Mike, to use the International Docking System Standard, just
Yes,
like we're planning
sure.
to use?
Yeah, that's already in development for ISS and for Orion. So we would use that docking system.
Okay. Any other questions before we? Okay, thanks. Thanks, Mike. Appreciate it.
Yep, thank you.
So our next presentation is from Douglas Ross from Lockheed Martin Corporation. And Doug's presentation is going to talk about an Orion mission kit that consists of a concept called a pantry module and a robotic arm that they would add to augment the initial mission concept. Doug?
Thank you. Good afternoon, and I appreciate the opportunity to talk with you. I'm from Lockheed Martin, and we've looked at a few options that could either help this mission or, again, help prove out technologies and capabilities for future options. As an introduction, both the asteroid retrieval vehicle and Orion will need accommodation for the human interaction that will occur at the asteroid. And so that will need to be factored into both of those designs, of course. The Orion mission kit could include a pantry module or a robotic arm system or both to help the exploration and support mission flexibility. And finally, I'll talk a little bit about the human-friendly features that will likely need to be incorporated into the ARV and upfront design and hardware flexibility that will make that a very versatile mission. First, the Orion mission kit increased stowage. We've looked at a few options that could allow additional stowage on the front end of Orion, and I'll show you one of those that has been looked at. The redirect mission will require attachment between Orion and the ARV prior to extravehicular activity. Current baseline is the NDS, will not need a pressurized tunnel. The mission may require extra stowage for the spacewalks, and there are several considerations on how to do that. The Orion launch mass is very important. Entry system mass needs to be within the acceptable range. Tool volume, pressurized stowage volume, docking requirements, sampling plan, and probably several others. Lockheed Martin has investigated several variations, both pressurized and unpressurized. One method of accommodation would be an external stowage module, which would give up to 2.5 cubic meters of space. Again, could be pressurized or unpressurized. This would be jettisoned prior to re-entry, and it would attach to the top of the crew module below the truss, and I'll show that in the next page here. Uses the existing attachment interface, and again, NDS or APAS compatible. This is what we envisioned. It sits right underneath the launch abort system truss, and during launch it's attached to both Orion and the truss so that the abort system could pull it off in the event it was needed. And I did want to point out that this is one concept. It just shows that the space is available, and there are several variations on what could be done there. A few features: it would provide a forward-mounted storage, which would be very useful and appropriately placed for the EVA activities. Could be pressurized up to 23 cargo transfer bag equivalents. And like I said, it would be closer to the asteroid, and if it's unpressurized, it makes it easier to get at those tools. If it were used with the Orion hatch, it could be open to either the crew cabin or or to space, so it could be a small airlock. Before I leave that last topic, I do want to mention that the docking systems could be such that the active side were on the front of the module and a passive interface on the aft end. So after the asteroid activity, this module could be left there at the asteroid for future work and have those tools available. The next chart here, another potential for the Orion mission kit is a robotic manipulator. Lockheed Martin and McDonnell Detweiler Associates have collaborated on a few studies in the past and looked at various arm combinations, and there are some possibilities that could be used here, and they could be mounted either on the Orion service module or the ARV, depending on what made the most sense and gave the most flexibility and essentially had the most mass available. There are some restrictions. Of course, it could not be mounted to Orion directly, and would have to consider structural mounting aspects, make sure that it was appropriate for launch loads. And you'll hear more about this in an upcoming presentation that MDA will give. For human-friendly ARV design, the ARV stage that returns the asteroid will require handholds, platforms, docking, grapple points for the astronauts. And we saw some of that yesterday in Steve Stitch's NBL charts. He showed some of those ideas in work. Design flexibility and simplicity, those will be key. Adapt to changing human interaction requirements both before launch and potentially during the mission. If simplicity and flexibility are designed in up front, it will allow the adaptation of the activity, the EVAs, potentially less scripted work, and things can be adjusted when preempted by new priorities. Lockheed Martin has been fortunate to work with NASA on several human-rated mission planning and crew operations, including the HST service missions, EVA operations and tool development for shuttle and ISS operations missions, as well as the Orion development. And refinement of the tool mock-ups early will be crucial, and I was glad to see this is already taking place. Designing for safety and flexibility, of course, these will be crucial for this mission, and ARV will need to be designed so that it's friendly and safe for the astronauts. This will, of course, involve more rigorous review and procedures and additional testing. So all of that will need to be factored in. Several examples of designing for servicing are shown there. There are key documents out. I'm sure that that folks are are aware of all those, and those are available. There are many lessons learned on designing for efficiency, human safety, advanced planning, operational flexibility that should be considered. I believe that a flexible approach for mass savings will actually help this mission, allow for different attach points, different configuration options, and as things change, the mission can be reconfigured. In summary, Lockheed Martin's drawn on many lessons learned working with NASA on crewed space missions and designing spacecraft and tools for astronauts. There are several options which can increase flexibility and add capability. An adaptable design and mission planning flexibility, I think, will be extremely important for ARM as the development goes forward. And early planning will enable several things, including late adjustments to nominal and contingency EVA plans. It will increase human safety and allow potentially greater achievements with limited resources. And that's all I have. Are there any questions?
Well, I have one question. Well, I think we have a question in the room, Mark.
All right. Blinded by the lights.
Hi, good afternoon. Just a quick question on the pantry module. Did you say that that could be either pressurized or non-pressurized if you leave it behind?
It could be. There are options for both, and you'd want to consider the long-term plan, what you're going to do with it. I would say if you're going to leave it behind, it would probably be unpressurized. But
Okay, so
could be both.
Okay, so you'd have to have some type of repressurization kit, or would you rely on the Orion?
Yeah, I think options exist for both.
Okay,
Yeah.
okay. Oh, good. Thank you.
Mhm.
Any other questions? Did you have in your concepts design, did you come up with a mass estimate for the pantry module? And if so, estimate the performance of being able to have Orion deliver it? Does that work out?
Well, I think that would be a challenge. That's a good question. The mass estimate for this particular concept was in the 300 kilogram range, but I don't believe that accounted for the docking systems, which of course you would need to add in. And you wouldn't necessarily need all that capability that was factored in, so it could be lighter.
Thank you.
How about questions from online? Joe?
Yeah, actually. So in your presentation, you stated that the mission does not need a pressurized tunnel. Why is that the case?
Well, it's because the crew does not need to transfer between Orion and the ARV. There's nothing for them to go to. It could be pressurized for easier crew access internally, but not necessary.
Let's see, Doug, did you have an estimate of how much stowage capacity in terms of tools and things like that? I mean, you had, I think, 20 some odd TBs, but in
Right.
terms of mass, did you scope how many kilograms of tools?
I'm not sure. That would probably be more a driver for the total Orion launch mass would determine that.
Okay,
Yeah.
so we have one more question from the room.
Speaking of that, I think I saw the MDA presentation you're referring to this morning. It was very interesting. Or is it on the agenda?
There is one coming up this afternoon.
Okay, I apologize.
Yeah.
Well, there
So-
was one this morning that had robotic manipulation, robotic arm technology.
Okay.
presented.
It may be similar.
And
yeah.
can you speak to stowage with regard to that?
Stowage
Yes.
of an arm.
Yeah.
Well, I think it would probably be best left or held until the MDA presentation, but if the stowage were on the outside of the Orion crew module, it would be probably along the length externally stowed, and conceivably an arm could be stowed in this space as well, although it would probably constrict the size of it.
Let's see, Doug, I have one more question.
Mhm.
You know, we've worked pretty hard with our mission concept to try to not impact the Orion design, the structure, and how the vehicle comes together. Have you guys done a look at, is this a big impact to the structure in terms of launch loads or any other kind of mission scenarios in terms of executing the mission?
As far as a pantry module?
Yes.
To my knowledge, adding a pantry module like this would not affect the Orion design. And that's one of the benefits of it. The space is available and could be used with minimal to no impact.
Okay, thank you.
Right.
Any other questions for Doug? Thank you very much, Doug.
Sure.
you.
Thank you.
See, our next presentation is Jonathan Robel. I believe he's an online presenter. Jonathan, are you there? We'll try one more time. Jonathan? How about we'll move along and we'll pick that back up later in our program. How about Aaron Parness from the Jet Propulsion Lab? Aaron, let's move to that presentation. And
Hey, can you guys hear me?
oh, okay. Are you there?
Yeah, sorry.
Sorry about that, Aaron. Let's go ahead, Jonathan. And your presentation, you have two presentations actually. The first we'll discuss anchoring, sample acquisition, and in situ resource utilization approaches for asteroids. And then that's the first presentation. So if you're ready, we have the presentation called up.
Brilliant, thanks. Sorry, I'm just getting a little bit of feedback here.
Okay, we'll take a second and whenever you're ready.
Okay, yeah, thank you. Good afternoon. Yeah, it's a pleasure to be presenting at the Asteroid Initiative Idea Synthesis Workshop. As you said, I'm Dr. Jonathan Robel, Senior Research Scientist at Honeybee Robotics in our Flight Systems Group located in Longmont, Colorado. Today I'll be presenting, as you said, on Honeybee Robotics technologies for cruise systems for asteroid exploration. And as I'm presenting remotely, again, please let me know if the audio is coming through clearly. As the schedule has me down for two sequential talks on cruise systems, I'll be rolling that into one that covers both anchoring and sample acquisition. All right. So before I begin, I'd like to provide a bit of background on Honeybee Robotics. Founded in 1983 by Steve Gorvin and Chris Chapman, Honeybee Robotics Spacecraft Mechanisms Corporation is a privately owned small business committed to developing high-reliability mechanical and electromechanical systems for the U.S. government, as well as for the private aerospace and space sectors. We have offices in Pasadena, California, Longmont, Colorado, and our headquarters is in New York. Wow, bad feedback. We are celebrating 30 years of developing space systems, and this has included a number of NASA missions. 2003, Mars Exploration Rover, where we worked on the rock abrasion tool. 2007, Mars Phoenix Lander, working on the TEGA dust cover and icy soil acquisition device. 2011, Mars Science Laboratory, robotic sample manipulation system, as well as the dust removal tool end effector. We currently have 6 gadgets on Mars and have successfully completed over 300 excavations on the Martian surface. We believe this work is helping pave the way for human exploration of Mars, and we hope to support both robotic and human exploration of asteroids in the coming NASA initiative. At this workshop, Honeybee is presenting a number of topic areas, including Topic 2, the asteroid redirection systems, Topic 3, asteroid deflection demonstration, Topic 4, asteroid capture systems, and Topic 5, cruise systems for asteroid exploration. And then not shown, Topic 6, partnerships. So I'll briefly touch on some of the technologies in these other topic areas, but focus on topic 5 for this session, crew systems for asteroid exploration. Many of these technologies can see dual purpose, which is why I'm going this route. The way we see our technologies, they enable us to interact with the asteroid in different ways, from helping us to better see it, if you will, to touching it and anchoring it and collecting portions of it. Oops, sorry, flying through this thing, the controls. So in regards to seeing the asteroid, we have developed laser-induced breakdown spectroscopy instrumentation, as well as 3D LiDAR. While the focus of the application for these was proxops and acquisition of composition information prior to engaging the asteroid, we believe that a portable LIBS system can be a very useful tool as a handheld or crew-deployed system when exploring the surface. LIBS works by using a laser to vaporize and ionize surface material, and when the plasma puff that you create cools and recombines, it will emit a spectrum reflecting its composition. This allows identification of surface materials without collecting them. In this way, astronauts can identify and selectively collect materials from the surface. We also have been working on technologies for impacting the asteroid. While not a crew system directly, impact our technology will be useful prior to engagement with the asteroid for determining its composition. Furthermore, it may provide a fresh crater for crews to explore and expose different material. And then in regards to touching the asteroid, well, the drill shown up here was originally designed for a touch-and-go surface sampler, where the drill and sample collection unit would be lowered by a tether to the asteroid surface. These can also serve as crew-operated tools. Much work will have to go to tailoring the sample collection instruments to the expected surface type and composition, or alternatively, the crew could be outfitted with a quiver of tools to cover a wide array of sample collection environments. So pairing that quiver of tools with a LIBS instrument or other rock identification system can help astronauts select the correct tool for the surface they encounter. Honeybee has also done work for harpoon sampling, and another technology worked on for robotic sample acquisition, the ARP probe, which would bring a sample back to an orbiting spacecraft, providing composition information before the parent craft engages the asteroid. This harpoon and drilling technology leads us to one of Honeybee's strengths, and that is robotic drilling. Honeybee Robotics has a long history with robotic drilling and sample collection, and a number of our technologies are suitable to the crew systems aspect of the Asteroid Initiative. These include the pneumatic approaches to sample collection, which is a robust method for sample collection, and as well as mobile in situ water extractor system, which will allow the selective collection of water. Focusing on drills, numerous robotic and handheld drills support the many tasks astronauts will need to do on the surface. Drilling is often the method of choice for penetrating hard rocks, and in a vast majority of applications, drilling employs the turning of a hardened bit forced into the rock, abrading small particles. Once the drill bit becomes dull, however, the rate at which the drill bit penetrates the rock drops dramatically unless an ever-increasing downward force, in the case of vertical drilling, is applied, and that's creating higher and higher frictional heat. The amount of this downward force is referred to as weight on bit. And in a low-gravity environment, weight on bit can be severely limited and must be provided by either spacecraft thrusters or an anchored base for the drill to push or rather pull against. Rotary percussive drilling action can be employed to circumvent the need for prohibitively high weight on bit. And percussive or hammer systems, while they consume more power, reduce the required weight on bit by an order of magnitude, especially in hard rocks. Honeybee has extensive experience with both approaches. Now, the feasibility of drilling into small bodies with low weight on bit has been tested using relevant analog rocks as stand-ins for the likely asteroid surface materials. Such testing demonstrates the feasibility of drilling into a small body with low weight on bit, but it's dependent on the strength of the materials comprised in the small body. Drilling in low-strength materials such as plaster or limestone is feasible using a commercially available drill with a 1.6 millimeter diameter bit with as little as 5 newtons weight on bit. Plaster and limestone have an unconfined compressive strength of 8 megapascals and 40 megapascals respectively, which would be representative of materials of a C-type asteroid. However, higher strength materials, such as those that would be representative of an S-type asteroid, cannot be drilled under those same conditions. For instance, 120 megapascal basalt is representative of the upper range of an S-type asteroid and cannot be penetrated with low weight on bit. This is not to say that it's infeasible to drill an S-type asteroid, but it does indicate that the drilling system must be designed with the target material in mind, have sufficient anchoring, and should be thoroughly tested ahead of time. We've also done work, what we call inhaling it. Many terrestrial applications use vacuum cleaners for picking up dirt and collecting material. The principle here lies in creating a lower pressure at the back end of a pickup hose than at the front, and thereby forcing the outside air to flow in and lost particles along the way. Now, such a system will not work in a vacuum of space. However, one can create a differential pressure by injecting gas into the regolith and then guiding this gas as it escapes from the regolith into appropriate pickup tubes. Shown left, we rely on injecting pressurized gas into the top few centimeters of regolith and then capture the regolith propelled upwards by the escaping gas into a transfer tube. Pneumatic approach can be ideally suited for obtaining both small samples for scientific analysis, as well as bulk samples for mining or processing of resources. And the working gas could be supplied by electrolyzing water into hydrogen and oxygen, so not incurring the mass burden for launch. For bulk regolith mining, a potential approach might be to use a system that has been initially developed for lunar regolith mining. The pneumatic regolith miner is similar to a conventional vacuum cleaner. However, instead of creating suction at the nozzle mouth, a compressed gas is injected again and moves the captured soil within the nozzle up the tube through the cyclone separator into a soil bin. Shown right is a pneumatic excavator integrated into the NASA Ames Research Center K-10 mini platform. System has been successfully tested in a 3-meter-long bed filled with GRC-1 soil simulant within a 3.5-meter vacuum chamber. We think that this could be a very useful tool in crews' quiver as they touch down on the surface and try to collect samples. Honeybee has also done work with the ability to snare items. This has been mostly focused in grappling with spacecraft in orbit for either in-orbit servicing or satellite deorbit. And our lasso technology can be used to either anchor to protrusions on the surface that are maybe part of a much larger boulder or the bulk of the asteroid, much like slinging a horn when rock climbing. And in this case, the technology can be used for either crew or spacecraft anchoring. Basically what you have is a lasso, as the name implies, that cinches down on a protruding rock, or in this case, in the series of images, that would be the thruster cone, the bell expansion nozzle. Now, as I mentioned earlier, it's important to be able to produce downward forces, weight on bit, and other downward forces. And Honeybee Robotics has a number of technologies to support the ability of astronauts to explore the surface of a captured asteroid, prospect for resources, and collect samples. And in this microgravity environment, anchoring their astronauts and equipment is crucial. Honeybee has a long history of anchoring and has developed a number of approaches, including hard rock drilling and hammering for setting anchors. And we've done preliminary feasibility tests yielding interesting results. Testing was performed with a 3-point 8mm nail and traditional hammer, as well as an off-the-shelf nail gun on 8 megapascal plaster and 40 megapascal limestone, as well as 120 megapascal basalt, so capturing the CNS type asteroids. The nail did not penetrate the basalt or limestone, but managed to penetrate plaster, which we would expect. And the nail gun, however, on the other hand, was powerful enough to drive a short nail into all 3 rock types. Now, this type of research is made possible by Honeybee's test facilities in Pasadena, where a large library of rock samples allows testing of drills and anchoring schemes in a variety of configurations and with a lot of instrumentation. Now, Honeybee has also worked on fluid anchors. That allows anchoring to featured surfaces with the benefit that the anchor deployment does not exert any force that would require a reaction by the spacecraft or the crew. In the fluid anchor approach, a wetting fluid such as foam, cement, epoxy is injected onto a surface or into the soil by a hollow spike beneath the footpad. And if applied to the surface, the goal of the fluid anchor is to inject an adhesive cushion between the rock surface and the spacecraft footpad or crew anchor pad, and in turn provide an anchor once it sets. If injected into the ground, the fluid would go deeper into the loose gravel or soil, allowing the anchor to gauge a larger volume of asteroid material, forming a composite footing, glue mixed with soil or gravel. The self-opposing multi-mode anchor, which is shown on this slide, allows payloads and equipment to be securely anchored to the surface with minimal applied force, mostly using the opposition force. So we presented a number of technologies that we think will be enabling for crew systems to explore the asteroid and interact with it. And as well, a large goal of the Asteroid Initiative is to capture and return an asteroid to the Earth's vicinity. With our extensive background in spacecraft mechanism and mechatronics, Honeybee Robotics is also excited to support the direct capture phase. With that, I'd like to conclude my talk and open it for questions, unless they're being held to the end of the session. And I also encourage you to visit our website listed at the bottom of this page to further explore any of our technologies and to contact us. Thank you.
Are there any questions in the room or online? It's very hard to see with the light. So I did have one question for you. On your pneumatic drill where you use the vacuum technology to capture the dust, how much does a tool like that weigh and how big is it?
I knew I'd get a question that was going to be a mess. And the thought I had on that is it's really going to depend on the application. Like I said, what you're going to be drilling into, how you're going to be anchoring in, and then, of course, what you drill into determines what material it is you're collecting. So, unfortunately, I'd say probably the best answer to that is a parametric study, but if you guys contact us, we can provide more details if you have a specific scenario.
I'll let you off the hook. Thank you much.
You're welcome.
Let's see, Joe, do we have any questions, virtual questions on this present? Well, let's see, I have a question, Jonathan. I'm intrigued by your self-opposing multi-mode anchor, and there's a lot of debate as to the consistency of an asteroid, ranging from a solid rock material to what's kind of called as a rubble pile or almost a sand pile, or some theories are some asteroids may be almost like a dried mud-like consistency. How do you envision the anchoring system working in a variety of asteroid environments?
Well, I think it depends how the mission evolves and what asteroids targeted. My understanding is that as you move towards the larger asteroids with the lower spin rates, the chances are you're encountering a rubble pile. There's the smaller ones with faster spin rates that likely fly apart. So I think as the mission evolves, you would hopefully have some ability to tailor the anchoring approach to what you expect to find. Or, as I mentioned earlier, for the crew systems, you kind of bring with you a quiver of tools. So maybe if this self-opposing anchor comes into contact with a very well consolidated, or let's say solid surface that's really not amenable to just kind of sticking a shovel into it and slowly, a pick into it and slowly anchoring in. Maybe you can use a foaming anchor, a liquid anchor in conjunction. So the idea would be to create something that overlaps enough where you don't have any holes in your scheme, anchoring scheme.
Okay, thanks, Jonathan. And I think we do have one online question. Wendy or Joe?
Yeah. Yes. So the question is, since most asteroid capture systems have a centralized hub, have you given any thought to how you might sample the rock from that point and then make that accessible to the crew?
I think that could leverage some of the, marsupial designs where we had done work with the smaller craft that would fly ahead to the asteroid surface to give composition information ahead of the bulk interaction. And so I think you could probably adapt those to ferrying material to you.
Okay, thanks, Jonathan. Any other questions?
Okay, you're welcome.
Thank you very much.
Thanks for the time.
Appreciate it. So our next presentation is from Aaron Parnas from the Jet Propulsion Lab. And Aaron's presentation will discuss self-anchoring microgravity drill for use to sample the asteroid. Aaron?
Yeah, thank you very much. I actually also have back-to-back brief presentations. The first one is more on a short-term development project. It's a tool that might be used EVA during the crewed portion of the mission. You can see a prototype of that tool here. It's a coring drill, and it uses an anchor to latch onto the rock to address the problems we were just hearing about in the prior presentation of that weight on bit. Since it's very difficult to test in zero gravity here on the surface of the Earth, we tested in these different configurations to try and cancel out the effects of gravity. So it's supporting itself upside down there, drilling into the ceiling on the vertical wall, or we lift the rock up off the floor and then drill into it. So to elaborate on the problem, this is Itokawa that you see. So there are big rocks there that you might want to sample from. But if you're using a typical drill like the one on the Curiosity rover, you need 50 to 100 newtons of force into that rock. And on a surface like Itokawa, where there's so little gravity, that means you would have to land over 1 million kilograms to react that force just with gravity. So we've got to come up with another way. The problem gets worse if you've got an astronaut who's pulling the trigger on the drill. You really don't want him to start spinning around the drill bit, which is just as likely in zero gravity as the drill is to spin in the borehole. So our approach is similar. We're gonna anchor to the surface that we want to sample from. This is a free body diagram of our gripper. It shows some claws that are grappling the surface of that rock, and that's what redirects the forces and torques of the sample back into the surface. So you can literally push the button on this drill and tell it to go, and it's hands-free. All the forces are closed loop in that rock. So the way we do our anchoring is using a technology called microspines. It was originally developed for wall climbing robots, and we've been working to adapt it for microgravity. It's a sharp hook, as you can see in the lower left picture, that's embedded inside some kind of frame with a compliant mechanism behind it. So it's basically a lot of claws on springs. And we use these in big arrays. So the gripper I'm going to show you in a minute has 250 of these distributed in a circle around the drill. Our path to flight design, which is shown on the right there, doesn't use any rubber materials. It's an all metal design. So it uses extension springs instead of these flexures in order to grip the surface. And there it is holding 30 pounds in a vertical orientation on, that's basalt, vesicular basalt. So you can see, hopefully online as well, this movie of one of these toes gripping. They're opportunistic, so you don't have to predict where the roughness is on the surface. You just put them all down and tell it to squeeze. And as they drag along the surface, you get a few of them to catch. So in that way, it's also probabilistic in that you don't need every single hook to catch. In fact, with about 10% of the toes engaging, we can support 100 newtons. And most of the rocks, I think all the rocks we anticipate seeing are going to be rough. The smooth rocks we see on Earth are usually processed by liquid water, either in a river or through glacial sort of movements. If we found very smooth rocks, that would be a remarkable thing in and of itself. So here's a video. Let's see. Oh, I think it's going to play automatically, I hope. There we go. Here it's going. So this is a video. Again, the drill is supporting its own weight, so it's got about, I think it's 3 kilograms in this configuration, plus the weight on bit, which in this case is 50, 70 newtons or so. That is a basalt. That's a vesicular basalt that we're drilling into. It's a rotary percussive drill. We actually just took a Bosch hammer drill and hacked it apart and put our own motor controllers on there as a proof of concept. The depth at which you're going to be able to drill and the width of your borehole is going to be just dependent on the power and the length of travel that you want to put into the mechanism. And you can see this is sped up about 8 times, but we progress at about 1 inch per minute in this type of basalt using a typical carbide bit. So it's a coring bit, so that's the whole point. You get to collect a sample. You can see one of the instances of our sample. I'm sorry, I should have a scale bar on there. That's a 1/2 inch diameter and about 1.5 inches long. Now there are also some operational assets that you have besides the sample. That borehole can provide a location for a permanent anchor. So the same way a rock climber puts in these clips on their way up the wall in Yosemite, an astronaut might do that onto the surface so that he or she could later come back and clip into that boulder as a secure point. So to cap off the status of this so far, it's a self-contained unit. It's robotic, so we have a set it and forget it mentality that the astronaut would place the drill and then wait 5 minutes or do some other task and come back and collect the sample. And we've designed it to be operable with big gloves. So this is one of our interns who helped a lot with this program, and he's got 4 sets of gloves on. So the path forward, we're looking to start to collaborate with the Crew Systems Office specifically, and anyone else that's interested, to take this to the next level. We think it's kind of a proof of concept now, and we need to up the TRL. So I'll take any questions you have on this tool. Thanks for your time.
Any questions in the room or online?
I do have one question.
Yeah.
Back on the drill concept, how much torque is required in the motor to actually perform that operation?
Yeah, so, it's something we should have measured. It's a 22-volt battery, and I'm not exactly sure, but I think we can get those numbers for you. Of course, that's also going to depend on the speed at which you want to drill and the loads that you're applying, and like the weight on bit.
Yeah, I was kind of curious, was it kind of the same variety that you might use on an astronaut's pistol rule?
Yeah, I think it would be very similar to that. All of those usually have 4 or 5 stage little planetary gearbox in there, and
Okay.
the motor's substantial, so it's a fair bit of torque.
Because you could maybe see a concept where you could take a device like this and maybe use one of these pistol grip tools and provide
Yeah,
torque
that would
and
certainly be a
that.
mass savings as well. I think that you could. The gripper itself only weighs 1.2 kilograms right now. Most of the weight is in that drill apparatus, so that would be where the savings would be.
Okay, thank you.
I believe you just answered my question, which is your current prototype is battery powered?
Yes, it is.
Good.
But lithium polymer batteries, so it's not
We
path
can-
to
we can
flight
swap
yet.
those out.
Yeah.
See, I think there's a question here in the front.
Yeah.
Yeah, thanks. You've shown a drill application, but on the screen, of course, there's another application. One can imagine all kinds of
Yeah.
applications for this. Can you talk a little bit about the letting go part too? So,
Sure. Yeah, so the little climbing robot there, photoshopped on the bottom, that's what I'm going to talk about next. It is a gripper that's meant to grip and release many times. We've tested that in the lab out to several hundred cycles. Because you have so many of these toes, if you lose a few of them, if a few of them break, it's no big deal. You're counting on this probability anyways. So we have an actuator to release those claws from the surface. So I will talk about that in the next one, how that happens, but it's an active release, and we make sure that actuator is powerful enough to actually break the claws off if need be to release.
Any other questions? Let's go on to your second picture.
Great. Let's see, is somebody else going to swap me over? Thanks.
So this is a mobile robot with microspline anchors.
Yeah, so this is addressing sort of some of the broader goals of the initiative, looking a little bit more long term. This would be a limbed robot that could provide a permanent presence, exploring the surface of an asteroid, demonstrating orbit alteration techniques, collecting samples, or preparing that asteroid for crew interaction. This was actually the initial part of the work. This is a movie, so let me see if I can, here we go. So this is a rock climbing robot we developed. We think it's the first rock climbing robot that's been built for natural rock. Here it is climbing upside down. This is some of the early work on these hand actuated grippers. So there's two actuation methods that are controlling over 750 of these independent claws, well, 3 per toe. And so the first actuator is shown here, pulling those claws off the surface. And so that's how we would release. The second actuator actually squeezes those claws inwards, as you're seeing in the video right there. And that's what loads them all up. That's what allows them to opportunistically find those rough spots to grip. So you might be able to see some of those stretching out. Now, rocks typically have a fractal roughness, so you need to conform at multiple length scales. So the individual hooks are doing sort of millimeter scale stuff. We have 16 of those in a carriage, and then, of course, the limb of the robot itself has some ability to conform to the surface. These are omnidirectional anchors, so we can tug on them directly away from the surface or directly along the surface, everything in between. And you can see the robot's got stereo cameras on the front there. We're also building in some force sensing into the grippers so that we know whether or not we have a good grip. We're also trying to learn how that grip is distributed, because there are some techniques you could use if you say only have the top of your gripper engaged and the bottom of another gripper. You can use the body of that robot to do a squeeze. You see rock climbers putting themselves into all kinds of crazy configurations to take advantage of the grips that are available to them. We'd like to get this robot to a point where it's able to do that as well. Now, this robot was originally built about 10 years ago. Brett Kennedy was the original builder. I got to JPL a few years ago. Nobody was using it, and so we sort of hacked it apart and added the grippers on. The sad news is it only has 3 degrees of freedom, 3 active joints per limb. So that's not enough to do really complex topographies right now. We're currently in the process of upgrading those limbs to 6 active degrees of freedom so that we can do things like plane changes and curving surfaces. I actually was out crawling around in a cave in the desert a couple of weeks ago, and we had a gripper, and we were hanging the gripper on the ceiling of the cave. So my dream to become a famous YouTube star is to get the robot to go around in circles inside the lava tube there. You can see a little bit more of the drill here and the operation, but I think I'm gonna skip ahead in the interest of time. So as I mentioned, we do have a path to flight. This isn't always going to be a rapid prototype and rubber band kind of system. This is the diagram of that path to flight prototype that we built. It's got the extension springs. Those are protected inside a housing so that debris and dust and things don't get in there and clog up the works. But again, it is a probabilistic system. So if you lose 1 or 2, it's no big deal. You have power in numbers. So here's that, testing in all the different orientations, about 30 pounds in each direction. We've tested on other kinds of samples. We use the Mars drilling suite of rocks, and we get more than 60 newtons on all of those. We've also tested on some granular surfaces. The idea would be to really anchor to the boulders, put in permanent anchor points, and then kind of tiptoe across the loose stuff and get to another boulder. And if you look at Itokawa and the other asteroids, that looks like a feasible concept of operations. So the overall benefits, we think this technology can enable alternative capture techniques. If you're going to grab a boulder off the surface, for instance, this could help. It could enable new kinds of deflection capabilities. You can position reflectors or explosives or thrusters at strategic locations instead of just where they fall down. You can get a lot of science return by, traversing large areas, but positioning your instruments very precisely and acquiring these core samples. And really my favorite version of this is as a precursor to a crewed mission where the robot is sort of scouting out locations of interest, but also setting up a network of cables that you've tested so you know that they're secure, so that when the astronauts get there, they don't have to worry about the safety problems, they can worry about the exploration problems. So again, thanks for your time. I'm happy to take questions. Yeah.
I was just curious what the initial face pressure for that gripper would be against the surface.
Yeah, it's a good question. It actually doesn't require any preload. Those carriages of claws are spring-loaded, so the operational sequence is to place the gripper in close proximity to the rock, but not loading it against the rock, and then you can activate. And so it doesn't require any significant force, and it doesn't tend to push itself away. It comes down and scrapes along because of the kinematics of those carriages, so it tends to self-grip. Yeah, that's a feature.
Any other questions in the room or online?
Not so much a question, but as a comment, but everyone seems to really enjoy the videos. I think your little robot's pretty cool.
Thank you. Yeah, you can go to YouTube and see it, and you get the most interesting comments there sometimes.
Well, I hope we help your YouTube career.
Thank you. Thank you.
Thanks, Aaron. I think one thing, this will, a lot of promise maybe on the drill for the asteroid mission, something that intrigues us, I think, as we think about it. And then personally, maybe I can become a rock climber with your devices. So thank you very much.
Yeah.
Thanks, Aaron.
Absolutely.
So let's see, our next presentation is Paul Fulford from MDA. He's going to talk about robotic manipulators, EVA tools, and collaboration between humans and robotics.
Great, thank you very much. The first slide is just an introduction to MDA and our past, and maybe just an overarching theme that the acquisition or capture of an asteroid is not dissimilar at all to capturing a spacecraft, be it cooperative or uncooperative. As early as 1981, the first Canadarm or SRMS flew on board the shuttle and did a whole series of different complex operations in terms of capturing very large, both cooperative and uncooperative spacecraft, as well as manipulating EVA crew. On the leftmost side, you can see servicing the Hubble Space Telescope. And then through the years and into the 2000s, we extended different capabilities for the Canadarm or the shuttle manipulator for its return to flight. We added appendages to do survey of the underside, which would be quite similar to that of an asteroid mission. We've provided sensors for the XSS-11 satellite rendezvous mission and provided the robots for the Orbital Express mission with Boeing. Through this last decade, and in fact in the last few years, the Canadian Space Agency's funded significant development on the next generation Canadarm. So we have different products that I'll show in a few minutes. And of recent, we've been doing a number of studies, in part with Lockheed Martin, trying to figure out how we can adapt our robots for
the physical characteristics of the Orion MPCV. So along the theme of this is really no different than addressing any other type of space vehicle, this slide just breaks down the concept of operations from you need to mate, you need to prepare the EVA crew for egress. The crew need to translate, be it on their own or with robots, to secure the work site, then to conduct different tasks, and here to collect samples. In terms of capability in Canada and at MDA, there are many high TRL systems that include the functions to capture and berth either an Orion to an ARV or an ARV to an Orion. The functions of translating crew, positioning, and providing the static stability or support when working, to provide both astronaut and tool stabilization, to do pre-site work and post-site. So the idea of doing preparatory or precursor or triage work with robotics, and after EVA to continue on doing so. Perhaps to follow on Aaron's presentation, a robotic arm could continue to do, say, deep drilling after the EVA operations are over. This slide, I'd like to say today's off nominal will be tomorrow's nominal. And what I mean by that is a lot of the operations to date on the shuttle and on the space station are heavily scripted, extremely rehearsed, well prepared. All of the what-if scenarios have been rehearsed, the neutral buoyancy lab tests, the validation of all of these operations. As we get further and further away from home, I think it's really important to understand that we need to abstract those operations up one level higher and be prepared for anything. And having lots of margin gives you lots of room to be prepared, but we don't actually have the luxury of that given the size of the spacecraft. But what robotic systems can do is they can provide flexibility, adaptability. Why don't we try this? Well, why don't we try that? So just to give you some ideas from the past, in the upper left corner is a thermal blanket repair on the shuttle. That was unplanned, and the crew members on a portable foot restraint on the end of the robotic arm. The middle one is the additional boom sensor that was on critical path for shuttle return to flight after the last disaster, and was used until the retirement to inspect the heating tiles underneath. The one on the right was affectionately called the fly swatter, which I think had to do with just adding an adapted tool to the end effector of the robot arm to support deployment of communications. In the bottom left is the most recent robotic refueling mission with Goddard Space Flight Center on the International Space Station, where the whole premise of that work is to look at uncooperative, unstructured, unplanned type operations, anything from cutting wires to removing both captive and non-captive bolts to cutting thermal blankets. The middle bottom is just to support science, and sometimes certain instruments, things didn't go as planned or the situation changed, so you could use a robotic arm to orient or locate a different spacecraft. And then on the bottom right is to survey solar arrays. Send the crew out where it's actually not favorable or appropriate to send an EVA crew member. So, okay, I'll just leave it there. So in terms of our latest and greatest concepts, since 2008 we've been working with Lockheed Martin, funded by the Canadian Space Agency, and combining the technologies we've developed for the next generation Canadarm, trying to figure out different ways to adapt our systems for future missions. And what you can see up in the top is our next generation Canadarm concept that has extendable passive booms. So by anchoring either end of the robot and commanding the joints, through that actuation, you're you're extending or retracting the booms to permit better storage. Now we're looking at lighter weight systems. To answer one of the questions earlier from one of the earlier presentations, we're studying the Orion vehicle. There's 3 possible areas right now to date. One is the pantry module. One is called a sim bay, which is on the exterior of the service module. And then there's a possibility for additional room inside the service module as well. Each have their own unique constraints. We're trying to study them all and come up with a solution that could potentially work in them all depending on the scenario. And so far it's looking favorable in terms of volume. We would still need to study mass and power. In terms of tools and aids, both the robots that Canada have built and the tools that Canada have built have accommodated a wide variety of tools developed not only in Canada but around the world. The robotic refueling mission is one example where there's tools developed at Goddard Space Flight Center that the robots can adapt to. And the whole idea of having a multi-purpose robotic system that's flexible and adaptable, modular, reconfigurable, all of those attributes I think will lend themselves quite well, and we've done a lot of different operations to date and will continue to do so. Some of the more novel ones with the next generation Canadarm have also dealt with satellite refueling and the transferring of fluids and stuff. And this is my last slide. And for those that weren't at the morning session, this could be considered a little cheeky, but it's also showing MDA's concept for an alternate idea for capturing of an asteroid. And this image is intended to represent the cooperative efforts between a robot and the EVA crew. And you can actually see that other structure where crew can climb all over those robotic limbs, and you can have a manipulator mounted to the Orion vehicle or to the ARV and provide tools, provide stability platforms to do different survey camera views, whatever is required. And with that, I'll take any questions.
Traditionally, the Canada Arm has been operated by an IVA crew member in support of EVA crew, and what I haven't seen here, under the premise that this mission would have 2 crew members on board, who's operating the robot? And, you know, hearkening to the European robotic arm, which at one point in time had an EVA operated capability on it, is that something that you would consider hosting on this mission as well?
Yes, so under consideration is the whole cherry picker idea, where there would be a control console as part of the portable foot restraint. That's under consideration. And I'm not sure if everyone is aware, but the majority of the robotic operations on the ISS are now done on the ground. So there's also ground-based operations where, if anything, they're done when the crew is asleep, to just offload their work processes on the station. So given the locations here, it would be quite feasible, especially using different varying levels of autonomy. You can have direct teleoperation, you can have scripts with supervisory control. All those different types of autonomy I think would support that as well. So you could have it on the ground if it made sense. You could have it in the Orion vehicle. You could also have a cherry picker type EVA crew member commanding and controlling.
There might be some combination where you use the ground to move it to some position, and then maybe the crew does some fine, you know, inch left or inch right or whatever. Other question about.
What do you think are the worst load cases?
Wait, Mike, please.
What do you think are the worst load cases when you're designing an arm like that for this mission?
Stopping a large mass. That would be the worst scenario. Either stopping its rate or its linear or all 6 degree of freedom translation, and that's tied to time. So what its rate is, how quickly the arm can move, how quickly it can capture, and then decelerate it to a 0 velocity. Those generate the highest loads.
Any other questions? I think there's one in the back.
I would just help you with the answer also to say that probably the highest load case would be testing it on the ground. Right, that ends up usually lots of time being the driver. You end up flying a heavier arm because you wanted it 1G testable or not. I know it's a classic trade that roboticists have to make.
Yeah, it's worth noting that many of our manipulators can't support their own mass in 1G environment. We have different means of verifying and validating that.
Thank you very much, sir.
Thank you.
Thanks, Paul. So our next presentation, this is a virtual presentation. The presenter is Dave Aiken. He's from the University of Maryland. And Dave's going to talk about a free-flying camera for asteroid inspection, tether systems to anchor the crew, and space utility vehicle. Dave, are you online?
I am online. However, I don't see anything on Adobe Connect except click here for troubleshooting.
Do you have the slides yourself? The slides are up here in the room in Houston.
Okay, let me just go. I'll tell you when it's. Okay, sorry, I'll just tell you when it's switched. So, what I'm going to talk about today, are you ready?
We are ready, thanks.
Okay. What I'm going to talk about today are 3 different appropriate technologies that we've been testing here in the Space Systems Lab at the University of Maryland that I think would have real utility in an asteroid mission. The second slide, the first non-titled slide, is one of these 3 technologies. We actually developed this for NASA and DARPA as part of the Spheres, the Inspire program, which was an outgrowth of the Spheres. And it was called Exospheres. And the intent is to come up with a small free-flying vehicle that is capable of being certified to operationally and routinely do sorties around the outside of International Space Station. We actually have teamed up with Arizona State and looked at the utility of a vehicle of this class at an asteroid as an adjunct to a human mission to do things like do magnetometer surveys and close inspection, mapping, and photomosaicing and issues like that. It's a 50-kilogram cold gas vehicle using CO2 as the propellant. We sized it for an 8-hour sortie at International Space Station. It has about 40 meters per second delta V capability total. We wanted it to be easily reconfigurable for particular missions. So the 50-kilogram vehicle is the core vehicle, and there are fittings on each end for what we call AMPs, which are advanced mission packages. So you can dock into one on the front and one on the back. We can also use that for additional capability in terms of more propellant and power for longer duration or longer distance missions. The configuration the top image shows is our space station inspection configuration with basically a suite of cameras both for navigation and for close inspection of the external structure of station. This would also be viable on asteroidal photomosaicing, and the Arizona State folks have come up with a lot of other instrumentation that could be put into mission packages. The system is capable of being based externally, refueling and resupplying autonomously outside. We can also change out the mission packages by itself, so you don't have to bring it in and play with it. It basically is good for multiple sorties. So we have a prototype not shown here, which is running on our air-bearing table, and we have a duplicate version called Euclid, which works in our neutral buoyancy facility and gives us the ability to do fairly high-fidelity extended navigation and mobility studies. So this would basically go with the crew to the asteroid and give you the ability to do a lot of interaction locally. We also think this is extendable to sampling. Under an Air Force program, we developed a very lightweight manipulator arm that would go nicely on an advanced mission package for this. It's 80 centimeters long, 7 degrees of freedom, and 5 kilograms total mass. And it's capable of simple sampling, instrument placement, and tasks such as that. And so that, I should say I'm on page 3 now, if you didn't figure that out. So that would be a useful tool as well. On page 4, we were interested in restraint and mobility at asteroidal gravitation levels. So this is a concept of a 3-point restraint to fixed locations and being able to have programmable tension in the cables to be able to adjust the downforce to whatever is appropriate for the task you're doing. You can see patterns down here that we've looked at for handoffs between cables to be able to maintain a 3-point restraint throughout. Effectively, if you have, depending on the size of the asteroid and the length of the cables and the topology, you can cover the surface of an asteroid with this sort of a restraint approach. Page 5 shows some underwater testing that we've done in our neutral buoyancy facility. So the test subject here is on a treadmill. We were actually interested, more or less as an ancillary research topic, of how low can you go in gravitational level and still reasonably use a walking or other two-legged gait for mobility. So what we have are 3 cables to the test subject. If you look carefully at the image, you can see little round dots on his legs and a green light that's showing through about at his belly button. That is a 12-camera Qualisys motion tracking system we have in the tank. So we can get sub-centimeter resolution at 50 to 100 hertz on an effectively unlimited number of targets. And that allows us to get very fine data on details of gait as a function of gravity, and which is basically the same as the level of downforce you dial in on the restraint system. So we've verified that this system works, and think that it's now actually we've talked about. I do a lot of collaborative stuff with the folks in the Astronomy and Space Sciences division here, Michael Ahern from the Deep Impact Probe, and Jessica Sunshine and those folks, and they actually are concerned that there's not going to be that most of these are going to be loose aggregates rather than rocks. So that's an issue that's beyond my pay grade. Slide 6 represents an instantiation of about 20 years of research on single-person, what we call space utility vehicles, largely to prevent them from being called man in a can, which I think is probably one of the reasons no one's ever tried anything like this. One approach we've taken after a lot of trades is to, unlike, say, Flexcraft, which is out of NASA Marshall, to basically incorporate hard suit AX5 type elements that allow us to maintain both particulate and, to a lesser extent, radiation shielding while providing the occupant with eyes and hands on task. So it's actually a hybrid system between the operator's hands and suit gloves and the robotic systems. So we've looked at this for a variety of tasks. Again, if you have shifting particulate structure to the asteroids you're approaching, this would be far safer than going up to it in a soft suit or hybrid suit in terms of making sure that you don't get trapped or you don't get have problems with impact. The other thing is I think a hybrid of this would make a great deal of sense as the asteroid exploration module people have been talking about. So the idea is rather than have it just be a module that has an airlock, it would be one that would support an airlock or be usable as an airlock. would probably have a pair of suit ports so you don't have to lock out on nominal operations, and provide a variety of robotic and wall-mounted arms for manipulation, so that you don't actually do an EVA unless it's something that particularly needs the mobility or extra flexibility of a classic pressure suit. That's pretty much what I was going to say in slide 7, that you could launch it with the retrieval mission. Orion could dock to it and use it as an airlock, also through the suit ports. You could detach from Orion and use it in pre-flight mode with the cold gas thruster system, or use it like a small MMSEV with one person inside supporting a person in a suit. The nice thing about a vehicle like this, because of the dexterous robotics, after the Orion leaves, you can use it in either autonomous or teleoperated mode to continue the exploration. Actually, if you get there, since it gets there before the crew does, you could teleoperate it to start the sample collection process and have a cache of samples ready when the crew gets there. So by my timer, I'm about out of time. The last slide is just a way of contacting me if anybody has any interest or whatever, and if I have time, I'd be happy to take questions.
Any questions in the room?
Yeah, I think we have time for one question. Or maybe one question from online.
Well, I have one question. On your portable camera system, the first technology you discussed, does that technology have the capability to be refueled robotically so that it can be reused time after time? Or do you have to bring it inside to reservice it with human interaction?
No, we have a service system designed. Actually, the particular design we have is for station, but it's adaptable to anything, so that when you dock to it, fluid couplings are made, electrical couplings are made, and you can recharge the batteries and resupply the cold gas system while you're docked.
Beautiful. So you said that the excursion vehicle was 50 kilograms. What's the mass of the docking system and reservicing?
Right now, it's probably about 200 kilograms, but most of that was was basically enough propellant to do something like 50 sorties on space station.
Thank you very much.
So it's most of the mass is in CO2 canisters. So if you had a smaller number of sorties planned, you could pare down the docking station considerably.
Great.
The actual interface is about 20 kilograms.
Thank you. Any other questions? Thank you very much, Doctor.
Thanks, Dave.
All right, thank you.
So our next presentation is Rob Mueller from the Kennedy Space Center, and Rob's presentation is entitled Electrodynamic Dust Shield, Pneumatic Regolith Wraith, and a Percussive Evacuation Shovel. So we're looking forward to hearing from you.
Great, thank you. Good afternoon. I'd like to start by acknowledging my co-investigators here, Dr. Carlos Calle and Dr. Jim Montavani. They're both in the Swamp Works, which is an innovation lab that we have at Kennedy Space Center. It's part of the Surface Systems Office. It's dedicated to lean development and providing new technologies for human and robotic space exploration. So this afternoon I'd like to highlight 3 technologies in our portfolio of technology development because they seem to be rather relevant to the Asteroid initiative. When the RFI came out, we looked at what we had going on. We said, well, these technologies seem like they would be very useful for a crew asteroid mission where the crew needs to have some help and possibly make the mission safer because we have never done this before. And so we need to make sure we don't get the astronauts into situations with the regolith and the rocks and the abrasiveness. One of the biggest problems in Apollo was the dust. So this is, in many of the talks this morning, you've heard that dust does exist on asteroids, and it's held down by van der Waals forces. And the combined forces of billions of small particles is actually quite high. So the same forces, electrostatic and van der Waals, can stick to your EVA suit and cause problems. So to solve that, we have a technology called the electrodynamic dust shield. And this is a series of electrodes embedded in a material, and it could be used for visors, optical devices, viewports, transparent electrodes on film, plastic, or glass. So you can imagine it could be used on the visor of the EVA suit, it could be used on camera lenses, it could be used on sensors. Anything that could be spoofed by dust or obscured by dust or regolith in general would be used. This technology would be useful. We've also been working to embed this. If you look at the upper right here, let's see if this mouse works so everybody online can see it. On the upper right, this is actually the electrodynamic dust shield printed onto a fabric. And so not only does it work on a solid piece of glass, which is what you see here on the top left, and then in the middle you see it's dirty, and then you flick the switch and it cleans it. That square is cleaned by the embedded electrodes. You can also put it on a cloth fabric, or you can put it on a flexible film. And we've tested this, if you look in the bottom right here, in a reduced gravity flight. So the TRL progression is significant, and we're almost ready to go with this now. In fact, it's going on Missy X to station in a couple of years, next opportunity. And at that point, we'll say it's a TRL 9, maybe 8 or 9. So this is an exciting technology. I do have a video. Let's see if we get lucky here. And we did. So here's the video. I hope you can see it online. And this is the results of the reduced gravity test flight. What you see, there's a vacuum chamber, which was on loan from Langley, and the crew is from Kennedy. And so with a collaborative effort between the two space centers, we tested this, and you can see those electrodes starting to work. Now, they're not on all the time. They just pulse, and every time they pulse, you'll see the dust moving. So right now you see that spiral pattern. The spiral is the electrodes, and then they pulsed it again, and now it's clean. So it's very efficient. And if you look at this in slow motion under a microscope, it's pretty cool because it's like ripples in a pond. If you throw a rock into a pond and the ripples move concentrically outwards, that's exactly what it does to the dust, and it just moves the dust sideways off of your optics. So that's one exciting technology we'd like to present today. The next technology we'd like to suggest could be useful in a mission like this is a pneumatic regolith rake. Now, you've already heard today about doing things with pneumatics. This was a technology that we developed in collaboration with Honeybee Robotics under an SBIR contract, and we've since taken it in our lab to the next level for this kind of application. And so what this does is people always have a problem with pneumatics and vacuum, and rightfully so. But what the key to this technology is the gas never actually goes out into the vacuum and is lost. The gas makes a small jet and creates a hole. Imagine taking your garden hose and pointing it downward in your garden into the mud. And it goes straight down, does a U-turn, and comes right back into your face. And that's exactly what this technology does. The gas goes straight down, and it digs a hole pneumatically, and it traps the little granules of regolith in the gas flow, and then it brings it back up, and you capture it in a concentric tube. So there's an annulus inside the cross-section of the tube, and then you capture that regolith pneumatically. And we've had very high efficiencies, 1,000 to 1 and higher, in a reduced gravity environment in a vacuum. So what we thought we'd do is, if you look at this picture here, it's a series of pneumatic tubes that can actually capture, each tube can capture regolith. And now if you take lunar regolith as an analog, the particles are typically under 100 microns, between 20 and 100 microns. 80% are between 20 and 100, and 20% are under 20 micron. The rest, only 5% of the rocks on the moon are actually bigger than 100 microns. So that's the distribution of the particles. Now, I don't know if an asteroid will be like that, but let's assume it is. Then most of the regolith sample that you want is actually a granular material. The rest are rocks. So we can kill two birds with one stone by having a rake, by taking these tubes, making a rake out of them, mounting them on a handle, and then the regolith will be captured by the tubes, and the rocks will be captured by the rake. And the nice thing about this design is you can put it on a handle, And if you look at that video of the Asteroid initiative with the crew going up the pole and cutting open the bag, you really don't want to get too close to that regolith until you know what's in it. So you could reach out with a rake and capture a sample, and that would be one enhancement for your mission. Another technology we have is a percussive excavation shovel. And so percussion reduces reaction forces. The biggest problem in outer space and reduced gravity is you have no reaction force. So you try to dig and you don't dig, you don't penetrate. If you had a robot, if you had a front-end loader like you have here on a construction site and you put it on the moon and you push the bucket of the front-end loader into the soil, the machine would do a push-up. It would not penetrate the soil because there's not enough reaction force from the actual weight of the machine in that reduced gravity environment. So what we found is that because it's a dry granular material, if you use percussion, the little particles are actually, for lack of a better word, jiggled around, and it creates a bow wake. And then by creating this bow wake, you reduce the excavation forces. Now it's a trade-off because, and the reason they don't do this here on Earth is because it takes more energy. So, but you have energy in space, you have plenty of sunlight, but you don't have reaction force. So this is a trade-off, a simple mechanical trade-off. By using more energy to use percussion, you can reduce the excavation force, and we found it's very scale dependent. It's very, the small implements have up to 90% force reduction, reaction force reduction. The larger implements, we've only been getting 50%. So it's very much scale dependent, and we're still learning a lot about that. But we thought if we took this mechanism, and forgive the cartoon here, but we just photoshopped this onto a shovel, and we think if we could make a percussive shovel, that would be very useful to an astronaut on orbit, or actually at an asteroid. So in conclusion, we think that astronauts working with asteroid regolith will need protection from dust and dust mitigation for payloads and instruments. We think that, just as Harrison Schmitt said in Apollo, he said dust and regolith are the #1 challenge of going back to a planetary surface, and we think that's correct. And so with the electrodynamic dust shields at TRL 6 now, and it should be available for mission infusion after it's gone up on Missy X. And then the pneumatic regolith rake is a lower TRL. That's just something we've been done in the lab, and we haven't pursued it much. It's just opportunistic, and that's TRL 3. The percussive excavation shovel is at TRL 4. And so I'd like to thank the Space Technology Mission Directorate at NASA, the Game-Changing Division under the Human Robotic Systems Project for funding this work, because this is a technology push. And many times people have trouble with technology push because they can't see how it will be applied. But this is a perfect example of something we developed, and now the application has arrived and we're ready. And so, or we could be ready if we were asked to be ready. So this is a good example of technology push meeting technology pull in a mission, and we think it's a great model on how to operate inside NASA. So thanks for your attention.
Any questions? In the back?
Yes, like a question on the electrodynamic dust shield. Now, would that be incorporated in the suit, or like, I guess I'm a little confused on how that would that be incorporated in the suit?
On the fabric?
Right. On the fabric.
Okay, so on the fabric, we're looking at actually printing it. You know, the EVA suit is actually several suits, right? It's a layered approach, and so this would be the outer garment. And I was actually looking at it out in the lobby earlier on. And I quizzed the guy pretty good, and he said it's a Teflon covered aramid fiber, and that's as far as I got with that. But so if it's a Teflon covered fabric, that's what you see there is a Teflon covered fabric, and we're trying to. It's very difficult because to get these electrode patterns to stick to Teflon is almost impossible. So we've been experimenting with that, and we have managed to get it to work. So the vision is that you would print it directly onto the fabric and then use it as the outer garment. That's the vision. Now, we're not there yet, and it's not proven yet, but that is, we've done little swatches, fabric swatches like this.
So it looks like you could incorporate this to different, if not the host suit, maybe different sections of it, and the mass or the required weight of this, would that be dramatic or
The mass is negligible.
negligible?
And the power, people always ask about power when they
That was
see this.
the next one, yeah.
Yeah, so I'll preempt that. It's let's see, let me get this right. It's low current, high voltage. So it's low power, but it is high voltage, but low current, typically that's pretty reasonable.
You, on the same chart, you show an application for a viewport or optical devices. Would that affect the transmission of light through the optical device?
Yeah, great question. This is Dr. Carlos Calle is the principal investigator on this, and I myself have quizzed him on this and said, well, don't you lose something? Because if the vision for this too is you put it on a solar power, a photovoltaic farm in, say, in the Arizona desert, and then it would self-clean itself. Actually, this technology was developed for Mars. It never did fly on Mars because of the TRL issues, but it was originally designed for the solar panels for Mars, which was a showstopper until the dust devils came and cleaned them off. So Carlos tells me that it's 95% translucent, so you lose 5% for that blockage from each electrode, and he tells me that's pretty good. And we're also talking to the camera manufacturers on wouldn't they be interested in having this. What they do today is they have a little CMOS chip in there, and they vibrate it. They have a piezoelectric vibrator, and they just vibrate and shake the dust off because it's internal to the camera. But this could be applied to terrestrial lenses.
So we're going to do one more question, and then we're going to move on. So if we could go ahead and do this one here in front. Wendy, go ahead.
This one in front here, yeah.
For the percussive shovel, is there a relationship between the granular size and the frequency of the percussion?
Yeah, so percussion is tricky, and it is very dependent on the granular medium you're operating in. And what's interesting is, well, first of all, it has to be a dry granular medium. So it cannot be wet, like a clay type of soil. No, it will not work because the particles stick with the moisture of the clay. But in a planetary environment, the regolith is a good candidate for percussive excavation because of this particle size distribution. If you go on the premise that regolith is crushed rock from a high energy impact, then that's just basic physics and geology. And so it turns out that in most places, regolith is in that particle size distribution of 100 microns and below. So that's a pretty nice granular medium. And then what we've seen when we dig with these percussive shovels, there's this thing called the Brazil nut effect. And the Brazil nut effect is where when you buy a jar of nuts and you open it up, the Brazil nuts are always at the top. The Brazil nuts float to the top as they get shaken in transportation. So when you do percussive excavation in a regolith simulant, which we have, a basaltic regolith simulant in our lab, you see the darker particles, the bigger particles float to the top. And you see this Brazil nut effect. So it's classic granular mechanics at work. And so I think your question is very good, but it does depend on what you're digging in. But turns out that planetary regolith is a pretty good granular material for this technology.
Thank you very much, Rob.
Thank you.
So our next presentation is from Doyle Towles from ATK Space Systems. And the Doyle's talk will be on telescoping booms for the translation by the astronauts and EVA tools on the asteroid.
Thank you very much for the opportunity, and I'd also like to thank Jose Guerrero, who led our RFI response, as well as Ken Steele, who provided the information on telescoping booms. ATK Space Systems provides small spacecraft as well as integrated thermal systems, as well as other components and engineering services to most of the major NASA centers, including Goddard, JSC, and JPL. For the obligatory capabilities chart, we have 25 years of experience supporting EVA tools for Hubble servicing from the deploy mission all the way through the 5th servicing mission. A lot of these tools and tasks were not designed to be EVA serviceable. but we designed special tools to be able to allow their astronauts to perform very complex tasks. And then we supported the Space Shuttle program as well as the International Space Station for both tools and deployable booms. And more recently, we have supported EVR tools, both for the robotic refueling mission as well as for the DARPA Phoenix mission. And you see some examples here for those tools that are either flying in the case of robotic refueling mission or being developed for the Phoenix mission. And lastly, our Pasadena office has spent 16 years supporting JPL in developing sample acquisition and handling systems. We supported the Mars Science Lab Chemin instrument development, as well as we've been doing planetary drill technology. And we have specifically looked at deep drilling. We're actually able to drill, we've shown in the field, to go down to 10 meters, and we have a system that can go to 20 meters, operating on 60 watts of power with a single bit all the way down through the hole. So we tried to put together all the things that would be needed by the crew. Obviously, there needs to be translation to get out to the asteroid. ATK has developed a telescoping boom, which I'll talk about a little bit more. We've also supported the Hubble servicing missions with translation aids that fit to the carriers that allow astronauts to be able to move out to the Hubble. And then you also need restraints, and we're saying to use the existing foot restraints that are available. And then lastly, you need to have a tool, the sample storage, and a toolbox to carry all those tools. So we've leveraged something that we developed for a proposal for a lunar toolbox. To give a little bit more detail about the telescoping boom, this is a design that flew both on the shuttle as well as supported the space station in its building process. We can hold many cycles on this thing. It can allow a lot of force to be able to deploy and retract it. You can also limit that force. It can be made out of either metal or composites. And it has a high torsion and bending strength. And then the design is very scalable. You go anything from 3 inches diameter all the way up to 30 inches. And it's already been proven to be EVA safe. And you can add things to it, whether it be cabling or fixtures. So for the toolbox, what we tried to do is think of all the tools that we might need and try to cram them all in there. And what we're showing is basically the toolbox that you can open on either side, and it has multiple shelves on each side. So on the top sections, you'll see that we tried to fit all the basic tools that would be used to actually remove rocks and so forth into those two sections. And down at the bottom, we said all the sample acquisition systems as well as the storage of those samples. So to get into a little bit more detail about the tools that might be used, one of the things we're doing is leveraging a lot of the tools we developed for Hubble servicing and other missions. And on the first one there, the rock capture clamp, that was actually a connector tool that was developed for Hubble servicing. What we're calling the rock crack pick is actually for manipulating small fasteners that we had to remove for special tasks. And then your typical hammer and chisel kind of tools that you might need. The rock lift jack tool is actually a tool that was used for Hubble, in which we might not have a handrail in the right location. We could actually attach this handrail. So we're saying we can use that same technology to be able to grab a rock that might be somewhat attached to the asteroid and pull it off. And then needing to do anchoring, you can use your typical rock climbing tools, or you can have specialized tools like this anchor clamp, which is also leveraged from Hubble servicing to be able to go into a crack that might exist in the asteroid and be able to anchor in, as well as the gripper type tool that Aaron was showing earlier. And then the contact surface sampling, if you had some loose particles on the surface and you wanted to collect those, this is using a tool that was actually used for the lunar missions. And giving it a nice long broom so that you can hold it out far away so you don't get the dust on the crew member. And then I think Steve set me up pretty well here earlier of having a drill that actually is driven by the pistol grip tool. And the size of the drill will depend on how deep do you want to go into the asteroid, as well as how many samples do you want to collect. We were leveraging a lot of the technology that was done for Mars Science Lab, as well as being developed for the Mars 2020 mission. And then lastly, to actually collect those samples and seal them, again, we're leveraging stuff that's being developed for the Mars 2020 mission, both by ATK, JPL, and several other contractors. And then lastly, you need to put those samples into some kind of storage container. So the Goddard folks would be disappointed with me if I didn't have an animation. So I'm going to show the actual drilling task. Now, either the gripper could be on the drill already, or it could be separated, and you could mount it and then put on the drill. Showing here that we would activate the gripper to be able to make sure that the drill is already anchored to the surface. The crew member could actually even let go, and then could drive the actual drill with the PGT. The sizing of the motor and battery power should be adequate for typical EVA activity. And this is showing a coring drill. As the flutes are going around the outside, the core is being collected on the inside. As you get to the end, the core breaks off, and then you can pull all of that back into your sample tube. And then the astronaut could go around to different areas of the asteroid, collect multiple samples, and then be able to actually take the sample container and put it either back into the toolbox or into some other separate container to be brought back into the cabin. So that's all I have.
Any questions? I had one for you. Can you elaborate on how your telescoping tube is articulated to extend, and whether or not you've considered the ability to add planetary joints or other joints for bends in the mechanism?
Yes, this one is it's electronically driven. However, it can be hand manipulated as well. And yes, there actually are examples where we've done articulating joints. I think the shuttle version actually had 2 joints.
Okay. Other questions? Okay, thanks, Doyle. Appreciate it. So our next presenter is John Limer from Space Systems Loral, and his topic is ARV with robotic manipulators and how that would be used to berth the spacecraft and assist TV and crew during a spacewalk.
Thanks, Steve. Good afternoon. I'm representing Space Systems Loral this afternoon, also known as SSL, as you can tell by our stylish new logo in the bottom corner there. After we joined forces with MDA, you can see that logo looks suspiciously like the MDA one. Anyway, many of you people will remember me as a very, very long-time fixture at the MDA office in Toronto, where we have the robotics and automation division there. I was chief engineer for all the space station robotics, the Canadarm2, the Dexter, as well as Orbital Express and some of the medical robots we have in clinical trials right now. When we joined forces with SSL, I moved from Toronto, where it's snowing today, to Palo Alto, where it's not going to snow ever. And in Palo Alto, we have a very large SSL factory there, where we have 3,000 very highly skilled engineers and technicians, where we make the biggest, the most powerful geo-communication satellites in the world. And so what we're doing is we're combining the expertise in our Toronto office, where we do robotics, as well as our Pasadena office, which is known for the Mars robots and now the DARPA Phoenix dexterous robots. And we're creating a center of excellence, if you like, in Palo Alto, where we have a very unique combination of a complete spacecraft manufacturing and design facility, and then all of this autonomous capability from these other offices, so that now we can offer the U.S. government a complete turnkey end-to-end spacecraft plus robotics system for in space. We can also offer the U.S. government autonomous vehicles and underwater vehicles as well. So that's our plan. Over the next year, we're going to grow a new facility there, basically, serving the U.S. government. And so one of the very first offerings out of that division is a response to this ARR, or the ARM RFI. And we're offering a complete spacecraft solution. So that handles all of the phases of the mission, including the crew support phase that we're talking about this afternoon. And as we described on the last day of September, our vehicle is a two-part system. The first part is a high-powered solar electric propulsion tug. It runs at 50 kilowatts. And for us, that's just the next incremental step in what we're doing on geosats. We've got 30 kilowatt systems flying and have been flying, 35 kilowatt systems in the pipe, and 50 kilowatt for us is the next step. We'll couple that with some electric thrusters, 40 kilowatts of those, and a whole lot of xenon, and you've got enough delta V here to do pretty much anything you need running around the solar system between asteroids. We've decided to make this a separate tug so that it can do other things. So we can get whatever we need to the asteroid and bring it back and all that, but we can also do other missions too. This tug is separable. It can join on to other modules or other vehicles or other types of vehicles to do other missions throughout the solar system. So that's that idea. The front end of this thing is a robotic servicing spacecraft, which has all the dexterity of the robots, but also the 6 degree of freedom maneuvering and the relative navigation sensing and the fault-tolerant computing so that we don't run into things and all that kind of stuff, so that it can be designed first for the asteroid capture mission, but also, again, later for other things. Satellite servicing is an obvious one that everyone knows that MDA has been interested in for years and continues to be interested in, along with other folks. And most of the technology that's needed for that, for satellite servicing, is also applicable to this asteroid mission. So our idea is, let's build these modular blocks that we can take the pieces of and then use for here, but also use them in other parts of the other missions. So just to go into the crew support part of this, the front end of this vehicle, the separable vehicle, as you can see in this image, is joined with the Orion vehicle when it shows up, has two sets of robotics on it. You can see the very long one, that's a 13-meter robot, and then there's a set of three slightly more dexterous robots. They're about 3 meters apiece. So going into the longer robot first, the idea there is it's long enough that it can reach out and touch the asteroid or almost touch the asteroid or place instruments towards the asteroid before we even capture it or deflect it, so that we can get a clue of what it is we're dealing with. And then once we do capture it, which could be a bag or any of the solutions we heard this morning, which could be helped by this 13-meter arm, it's long enough that it can actually reach most of the surface area of the type of asteroid we're talking about. It can also help the crew gain access to the surface of that asteroid once it's back in moon orbit. One of the other benefits of this is that because the robots are all on the ARV, which is just one solution, and we heard earlier in this session, we've heard different solutions about where those robots can be, is that we don't have to burden the Orion vehicle with the robots if we put them on the ARV, or at least our servicing vehicle, and of course they're available for other missions. Also, it will allow a very low impact berthing if we like. For example, if the asteroid turns out to be nothing but a dust bunny, then when the Orion comes to dock, rather than having the impulsive docket forces, we can reach out with the arm very, very gently and do a very gentle berthing, which can, of course, cause a lot less disturbance to the dust bunny that we've got. And then the second set of robots, which are the 3 more dexterous robots. Let me just see if this, oh, there we go. So these 3 robots down here, a very similar sort of intention with those, in that they can handle instruments prior to the crew doing their sorties. They can do very repetitive type things. For example, a RAM inspec. You could do a complete survey of some area at 1 millimeter type increments that was chosen by the ground scientists prior to the crew going out, getting information. The crew can then go and do more related science with those. Or once the crew, or the prospectors, I'll call them prospectors for now because that's really what they're doing, once they pick interesting spots, then these arms can handle the very tedious exercise of analyzing them or positioning instruments around them or collecting samples or anything like that, as we heard a bit earlier today, controlled from the ground, because there's no reason that we can't do control of all of these robots from the ground with a set of scientists looking over somebody's shoulder saying, yeah, I want that, and we can go and do it. And so really what these robots are about is assisting the crew, taking the repetitive tasks associated with prospecting away from the crew so that they can go and do smarter things and pick better sites and look at interesting things to look at later and that sort of thing. So the benefit of these two sets of robots that we're talking about today is that they already exist. So in the top right corner there, you see the 13-meter arm. It was designed and built to capture the Hubble Space Telescope back in the mid-2000s when there was a fear that the Hubble Space Telescope was going to enter the atmosphere and make it to the ground, basically. And we were going to do a robotic rescue mission. So that arm has bits and pieces stolen from the other space station arms. The joints are from the Dexter robot. The motors are the redundantly wound motors from the Canadarm2. And the end effector is from the Space Shuttle arm. And we can replace that with any other end effector because unless asteroids come with grapple fixtures attached, in which case our capture problem is solved, we can put something a little more appropriate for this mission on there. The electronics have been updated. Canadarm2 uses 186s and 386s, believe it or not. We've upgraded the avionics on this particular one to RAD 750FXs, which means you can do more advanced control algorithms, and most importantly, we've got a natural feature-based machine vision algorithm running on that thing. What it means is a scientist on his screen can say, I want you to move me there, and he puts his cursor somewhere, or his mouse with his mouse, and the arm can go there. That's a very powerful way of graphically commanding robots to do things you want to do. For the dexterous arms, we're proposing copies of the DARPA Phoenix friend arms. They were designed for satellite servicing. They're very dexterous, and they would be perfectly capable of doing this kind of a job. And so for my final slide, I just want to remind folks that robots are not here to replace people, especially highly skilled people. What they're here to do is extend their capabilities and make them, allow them to do things that they couldn't do before. And we've proven this again and again. With a robot, with the crew, using the best of them both, you can do pretty amazing things. And I think this is a perfect example of where we can do that. I think that's it. Any questions?
On the 13-meter arm, I think you used the word soft berth.
Yeah.
Okay,
Yep.
so if that was a like a rubble, say, or a sand pile, how does that work without dissipating it or moving it? I mean,
yeah. What I have in mind is rather than for the docking mechanisms, you need a certain amount of impact or impulse, if you like, to make them, to trip them. And that gets transferred to everything in the stack. In the case of capture and berthing, the Orion would station keep some distance away from the ARV. For argument's sake, let's say 6 meters. That's a nice, safe distance. The arm would reach out very gently, because we can move this arm. We have the ability to shape the command, so the acceleration, deceleration, transfer of momentum, and all that can be very well controlled. You can move the arm out there, capture the station-kept Orion, and move it very gently into a berthing fixture that, rather than needing force to join with, can more or less just be placed into its capture envelope, and then the mechanism just closes. And there's no forces going anywhere in that case.
Any other questions in the room or online?
Thanks, John.
All right.
So our next presenter is Frank AIISW. If I butchered your name, I
That's fine.
apologize.
Thanks.
I'm German as well. And his presentation is from Oceaneering Space Systems, and he's going to talk a little bit about their EVA capabilities.
Yeah, well, that's presumably what I would talk about. When I was asked to write on the topic of this RFI, I wasn't really sure whether to paint with a big brush or a small brush. So I'm approaching this topic with a relatively large brush because the time that we're at in the formation of this mission, this initiative, really, I think this is the time to pursue rather large ideas. So next slide, please. We talk about the concept of tools. In the upper left-hand corner, you'll see an image that you're probably all familiar with from 2001: A Space Odyssey, where Ape throws a bone up in the air, and before you know it, we're looking at space stations. The message here is that all these pictures that you see are essentially tools all the way up to the scale of an aircraft carrier or a space station. We're really talking in very broad terms about what technologies we will apply to let humans do the best job possible exploring asteroids, not only on this mission, I think, but in the larger sense, what happens later. This, I think, is expressed as an asteroid exploration initiative, not necessarily a mission. And my question to the group in general is, when are you finished? It's very important when you look at tools to know exactly what it is you're going to do with these tools before you get started. I mean, I think we know at this point we need a toolbox. What it's full of is going to depend on what we intend to accomplish at these asteroids. And without knowing what we're going to accomplish, we have to really start off with very general capabilities like drilling, like picking, like grabbing. And as we learn more, as we penetrate further and further into this quest for knowledge about asteroids, we're going to come to know much more about what kind of tools we need. And on recurring missions, I think it's important that we build capability as we build knowledge on what these tools are supposed to do. That's why I was so refreshed to see several concepts today with regards to enhancements to the architecture that occur over multiple missions, so that at some point maybe we end up with an asteroid repository that could satisfy the investigation of many asteroids over multiple missions. And when NASA takes off and does the next great thing, that this asteroid laboratory in lunar orbit continues to serve some function and continues to allow people to build knowledge, not of just this first asteroid, but of subsequent asteroids that might be collected at this laboratory. So in addressing these unknowns, we need to retire the unknowns progressively. And I think it's going to take more than one mission. I think this initial mission, great, we can demonstrate that we can go get one. We can bust a chunk off of it. But just like, you don't build Hubble to look at one star. I don't think you build this architecture to look at one rock. I think you build an architecture that has some forward compatibility. Another thing I was asked to look at from Oceaneering's perspective, we have worked somewhat with some environmental control life support systems. We're developing a new suit, and we work a lot with EVA tools. So we're looking at architectural approaches that could reduce the overall mass of EVA capability. And one of those things would be to tailor the capacity of EVA and tailor the capacity of your environmental control systems to match the number of crew days on a particular mission. Another thing that could be done to reduce the overall mass of the EVA system would be to forego the use of a PLIS and support your suited subjects using umbilicals that are slaved from the spacecraft ECLIS system itself. You could then consider basing those umbilicals on the asteroid recovery vehicle rather than on the Orion itself, so that once you have the umbilicals in place, they remain in place. You don't need to fly them up on a repeated basis in order to have that light, essentially low transported mass approach to supporting EVA. Assuming that both EVA crew members are operating in a relatively common workspace, you might have a dual user umbilical, which would be similar to in surface supported diving. If you have one hose going down and splitting off to support two divers, you end up carrying a lot less hose. So there are generic ways that you could reduce the overall transported mass to support EVA in this particular type of an operating environment. And then the question arises, do you EVA or don't you EVA? And I think naturally on the earliest missions, when you're taking your baby steps and you're learning what it is you want to be able to do, EVA is going to be extremely important. But over time, I think automation, technology, and robotics is going to allow us to do a lot more and a lot more detailed exploration as we understand what challenges we're trying to face. So at some point in time, we might not have to go to this asteroid repository with people at all, or it might become a man-tended or a robotically tended asteroid laboratory, if you will, and no longer have to host EVA. So if we look at the accelerating advancements of extravehicular robotics and the time frame by which this mission might fly, we may find that we should be designing with transparency to the influx of much, much greater robotic technology within the next 10 to 12 years, let's say even. We can then look, as some people have described, at integrating the robotic capabilities into the asteroid recovery vehicle rather than hosting them on board the Orion. I think these particular robotic capabilities are going to be tailored to this particular work environment, and in the interest of not scarring or changing the Orion design to any great degree, we should really look at hosting all of those capabilities on the asteroid recovery vehicle to the greatest extent possible. Let's see, what else have I got here? We talked about hosting stowage and putting capacity on the resident assets at the asteroid. And if we're looking for high efficiency packing, for example, someone talked about putting 27 CTBEs someplace. Well, CTBs have not traditionally been extremely high efficiency packaging. If you look at the lower right-hand corner, you can see that a Progress vehicle uses custom tailored packaging for each particular nook and cranny in that vehicle to get the maximum amount of volume, useful volume in terms of, not space filler or not padding, not foam, but tools. So we should really be looking for ways to increase the efficiency of our packaging approaches. Along the left side, you'll see some ad hoc, highly efficient means of transporting things. People in other parts of the world have a different approach for how to be efficient. One guy even carrying a cow on board his motorcycle. It's not something I'd suggest we do, but I think we can become much more efficient than we are in packaging. This concept was talked about earlier, the idea of putting some sort of a adapter in between the asteroid recovery vehicle and the Orion, or building capability into the asteroid recovery vehicle. In this case, I refer to it as a closet where you could cache things. It's very important that we recognize as people go on these missions, there are going to be contingencies that they have to protect against. That might be in terms of carrying additional food, might be in terms of carrying additional supplies. But as you retire the risk during that mission, during which those particular assets are going to be of value to you, you can say, hey, we don't need this anymore. We're going to leave this stuff here. And it'd be nice to have a closet to put it into where you could leave it behind for subsequent crew members to use. We've talked about functional allocation amongst various spacecraft. I think it's also important to look at functional allocation among serial missions in an overall series, in a campaign of missions, and recognize that what we're really looking at right now is the challenge of getting off the dime on exploring asteroids. But we need to look at this as a multi-decadal thing. If you really want to achieve efficiencies at the broadest level, things that might not look efficient at a mission-by-mission level, you may realize that efficiency after 3 or 4 missions, or over the course of an entire multi-decadal campaign. So this really gets down to the point of whether we're looking to optimize at a very global level or whether we're looking to optimize at a point mission level. And that, you know, as the strategies for this entire initiative formulate, we need to look at what level do we really choose to optimize this architecture. That's all I have. Thank you.
We have time for one or two questions. Go ahead, Joe.
So the question was, wondering if you could expand on what you mean by extending the reach of umbilicals. Are you talking about longer umbilicals or what?
Yeah, if you had long enough umbilicals that you could support an EVA to the farthest reach away from the Orion vehicle as possible. And there are some limits to how long you can go with umbilicals before you run out. You just run into too much overhead in terms of fluid pressure and things like this. But that's what I was talking about, is extended length umbilicals.
Do you know what that practical limit would
No, I don't.
So I can actually answer that question. So we did do a trade study on EVA umbilical length versus going to the plisses to determine what the manifested umbilicals were on Orion versus if you look at the umbilicals that were used in Skylab, which were rather lengthy. And it actually turned out that the use of the plisses was lighter weight because of the length of the umbilicals, the mass of the umbilicals, and the pressure loss as you talk. So several of the topics that our speaker brought up were the exact trades that we were doing. So I very much agree with some of the questions you were posing.
Thank you.
Thanks, Frank. So we have one last presentation before we'll take a break, and that presentation comes from Ben Reed, good friend and colleague from the Goddard Space Flight Center, and I think Ben's going to talk to us about some of the things they've been working on in terms of EVA systems and robotics up at Goddard.
Thank you, Steve. Thank you, Mark. And while I've got my thank yous out, I've got the program for the folks that have gone before me. Let's see. Thank you, Doug, for talking about the docking system on HST. That was good working with you on that. Paul, RRM, thank you. It was we could not have done it without the Dexter and SSRMS, so thank you for your help there. Doyle, PGT, all the tools you showed for ATK built for all the Hubble missions. It was great working with you on that as well. John Lyman, the 13-meter arm for HRSDM. It's too bad we weren't able to fly that, but when the crew came available, we had to go with the tried and true. And Aaron, looking forward to getting one of your tools at the end of one of our robotic arms in the next couple weeks. Okay, next chart, please. Let's see. All right, so you all have heard this throughout most of the day. I was going to talk about the advantages that robotics bring to some of the problems we have here, right? We've got, we always have mass problems. We've got limited EVA time. We've got signal latency because of the distance to it. This is a really hard mission. And I am incredibly proud and happy to be helping any way that I can or that we can at Goddard to help the agency do it. It's our job to do the tough things, and by golly, when someone chose this, they were not lacking with hard things to do. So some of the advantages that robotics brings, you've already heard. Multiple dissimilar technologies for capture. If it's a rubble pile as opposed to a monolithic, very cohesive structure, different tools that are picked up or let go with a on-orbit tool changeout mechanism allows to have failure attempts, but with still a possibility for success. It's not one and done. It also allows you, once you've got the asteroid and you're on the long cruise back to Earth, I believe that's what, several years before we get back, is that right? So during that time, rather than just be cruising and having the astronauts train for multiple possible scenarios once they are present with the asteroid, it allows get-ahead work. We can pick up sampling, coring tools, the drill that we've seen in a couple of these talks, to get a sense for what is the consistency, what is the chemistry, so that we don't have to waste EVA crew time for multiple scenarios, but rather just the one that's going to present them. Augmenting EVA crew member efficiency, we talked about that, or several people have prior to me. Translation aids, I believe, Mark, it is 2 EVA days with a break in between, a day off. So in that day off, right, they set it up to drill in a particular spot with the techniques we've seen here today. And so they don't have to be out there holding the PGT if they don't want to, if that doesn't make sense. Robots don't fatigue as quickly as a crew member's arm does, and as we heard with previous talks, let them do the hard, difficult work that require, you know, a human being present. So we presently are working to purchase an engineering arm with a path to flight. We are roughly 1 year from receipt of this engineering arm. You see it here, and it is from a previous, most likely will be from a previous presenter that you've seen here today. It does, we do leverage off of the tremendous successful heritage of the Mars arms that are up there right now working well. DARPA spent a lot of money developing this arm, and we picked it up from where they left off and have continued to improve on it before we placed this procurement. Out at the end, you see the tool drive system. We'll talk about tools on the next chart. And we are working on our software system. About half of the money we spend on this program, you never ever get to see, and of course that is in the software. So we have not ignored that in the beginning. We are well on our way towards having a system that will be robust to unstructured environments. And I don't think you get any more unstructured than an unknown asteroid. So, tools, you've already seen this tool in a couple of charts. This is one of the tools we have up on RRM. This tool comes from a lot of Hubble tool heritage. One thing that we were forced to do with RRM, which was a module that's up on Space Station now, is 18 months from concept to launch. We didn't have a lot of room, we didn't have a lot of mass, but we wanted to do lots of things. So it forced us to fly nothing but multifunction tools. There is no tool on that module that does one thing. The tool you see in the bottom right hand corner here is what we call our wire cutter tool, which, guess what? Cuts wire. But it also is a parallel jaw gripper. You see here. And it has a blade that extends out of the tip for slicing thermal blanket tape. So this does at least 3 functions nominal in this tool when, as designed. So we think as you are limited in mass for the EVA tools, or we are, that we want all of them to be as multifunction as possible. Practicing on the ground. So we NASA have gotten ourselves into situations in the past where things didn't go exactly as planned, such as the capturing of satellites for repair in the shuttle in the 80s. So we tried to read well the lessons learned from those missions and develop our technology development campaign with that in mind. So we have spent tremendous amount of time and effort on producing motion simulation platforms for contact dynamics. So you see in the bottom here, we performed a high fidelity, near real time. I say near real time because there was a 20 millisecond delay between contact and motion. And it took us a good 9 months to drive that from 80 millisecond delay to 20 millisecond delay. But we are now at about 20 millisecond for full 60 degree of freedom contact dynamics, so that we can practice again and again autonomous capture either of course, a satellite, which is where we spend a lot of our efforts, but as well as asteroids you see in the top picture. And with one-touch software reconfiguration, it's easy to change the inertial properties of the client from 100 ton to 10 tons to 1,000 tons, spherical, non-spherical, to see how that would affect your tool, your capture technique, or your drilling technique, whatever it is you happen to be working on that day. We also have a modeling simulation laboratory that we call Free Space. And this is where we bring together modeling techniques to simulate what's going to happen. I won't read all the words on the chart. I know we're a little behind, so I'll go through this quickly. But in the bottom right-hand corner, you see this. The left-hand image is an image that we produced, a synthetic image of what Hubble would look like from a camera doing autonomous tracking during the last Hubble mission. So this is what we trained our cameras against. And during the mission, we used our natural feature recognition algorithms with the visible camera in the back of the shuttle on STS-125 to autonomously track the two vehicles coming together. And you see how closely they match each other. So this is the type of thing that we would do for an asteroid mission. We put in the synthetic imagery, and that's what you see in the upper right hand of an asteroid, to train our natural feature algorithms against before we do it for real in orbit. So we stand by, eager to help the agency with whatever path it decides to go for this mission. Thanks for your time. Thank you.
We have time for one or two questions for Ben before we take our break.
Could you say a little bit more about the arm that you're getting ready to procure?
Sure. It is, I believe, Bo, correct me, 2.2 meters tip to tip, from shoulder out to the tip. So it's got two 1 meter segments roughly, 7 degrees of freedom. As you saw at the software there, it does have collision avoidance, workarounds for singularities. Because we have originally developed this arm, once we took it over from DARPA, for satellite servicing, we are very much interested in compliance control during contact, right? So we're going to go up against a client satellite that's around 1,000 kilograms, maybe 2,000, maybe 4,000, reconfigurable. And we're not going to be touching it through the center of mass. We're going to be touching it on the side, probably where the Marmon ring is. And so being able to autonomously track the tip of the arm to reach out and touch it and not impart too much loads into it before we close the grasp has required close coordination between the machine vision algorithms, the camera system, the speed of the arm. We talked about the speed of the arm being one of the limiting factors in orbit. And the compliance control so it doesn't impart too much load. So all of that work has been ongoing for several years now that has led up to us putting in getting the paperwork together to go out and purchase an engineering arm. We do have a posable arm in the lab now. It was delivered since I came to Houston a couple days ago. So it's just freshly arrived. So it's a life-size, full-scale articulating arm that we will be using for reach and access studies over the coming weeks, months, and years. And if any of you are ever in the Washington, D.C. area, I encourage you to get in touch with me and come on out. We'll show you what we have in the lab. We like to give tours, don't we, Bo? Yes. Any other questions?
All right. Thanks, Ben. Thank you very much.
Thanks, Steve.
So Mark and I have been sitting on these chairs for 2.5 hours now. So we're going to take a break here in Houston for those online or participating via NASA TV. For those in the room here, let's try to be back in 10 minutes, and we'll resume at 4:15 p.m. Central Time.